Welcome back to eCoreAcademy students. My name is Anita, and I am one of the teachers and co-founders here, along with my younger brother, AJ Raj. Today, as you can see, we have a new Algebra 2 lesson for all of you. I know it's been quite a bit of time since eCoreAcademy has released an Algebra 2 lesson, but these lessons are extremely important, and this course is a very important course in high school math, so I wanted to get right back on track with it. Today's lesson is going to be introducing you to our newest unit, which is on polynomials, and today's lesson is going to be polynomial functions. This is going to be part 1, in which I show you information and notes that you're going to have to understand, pretty much going to be setting the foundation. And in the part 2 of polynomial functions, we're going to be doing some practice problems. So I thought it's best that we split this lesson up. This first lesson up. The first part, this part's going to focus more on notes and information, background, etc. And then the next video that's going to come out from Algebra 2 is going to be practice problems on polynomial functions. So in today's video, we're going to look specifically at polynomials with degrees greater than a quadratic. To explain this, let's go back in time a bit. The first unit in Algebra 2 was essentially linear equations, where we were focusing on equations like y equals mx plus b, where that x value is raised to an exponent of 1. That's why it's called a linear term. Then we would focus on quadratics, such as y equals ax squared plus bx plus c, which is standard form. And if you saw, if you've seen in the past videos, we worked with equations where the x term was raised to a power of 2, so it was x squared. So we're working with x squared terms, and hence it's a quadratic. From now on, we're going to be working with polynomials as in equations that have exponents that are greater than 2. So we're going to work with cubics, where we're going to have things with we're going to have polynomials with x to the 3rd power, quartics, x to the 4th power, quintics, x to the 5th power, and you might even see even higher exponents. What we mean by degrees greater than a quadratic, degrees mean exponents. So x to the 3rd, that 3 that's in the exponent is considered a degree. So it's pretty much a 3rd degree. For example, with a quadratic, it's x squared. So it's a 2nd degree. That's what we mean by degree. We're going to look at their graphical behavior. We're going to be looking at it primarily on the TI calculator, but I'm also going to show you how to graph it with a pencil and a pen, and in this case, a digital pencil and a pen, because a pencil and paper, because you're going to have to do it in the classroom. And lastly, we'll look at some XY tables to see how values of the function change over the domain, how the range, the relationship between the range and the domain for each polynomial function. Before I get into the video, I would really appreciate it if you all could like the video, subscribe to the channel, and hit the post notification bell. Also drop a comment down below and share using all of our socials. Let's get right into the video. Here's a quick overview of some key things that you're going to need to know. Here are the key ideas that I want you to keep in mind as we go through the lesson. The first part is we're classifying polynomials. When you classify something, I like to think of it this way. It's really through a scientific scope. You're kind of organizing it relative to other information. So you're pretty much trying to look at these polynomials. You're going to see these equations. Try to give them a name, a label, something that you can use so it becomes a comparative type of data so that we can compare it to other equations that we look at. So by classifying polynomials, we're pretty much identifying them, renaming them, and then organizing them. We're also going to be graphing these polynomial functions. I'll show you how. Primarily, if we're going to be using the TI calculator, we're just going to put them in our y equals. If we're not, we're just going to be using an XY table and just putting in x values, getting those y values, and plotting the points. We're going to be graphing the polynomial functions in order to look at end behavior. End behavior we're going to define later on, but it's pretty much how when you look at the very ends of the graph. So if this is my screen or this is my graph and I look at the very ends of the graph, what way does the function go? Does it go up? Does it go down? Does it increase? Does it decrease? We're going to be answering those questions. Next, let's look at how we're going to classify polynomials. We're going to classify polynomials by looking at the degree of the polynomial and or the number of terms. Remember how I said the degree is the exponent that the polynomial is raised to, and I'll give you a better example when we define exactly what degree is. So the degree is the exponent of each variable. The highest exponent is the degree of the polynomial. So I think the best way to explain this to you all would probably be showing you an example of a polynomial. So let's say I have y equals 7x squared plus 8x minus 1. So I'm just coming up with this off the top of my head. In this case, we're going to look at the exponent of each variable. We know the exponent is this little number up here. It's what this variable is raised to. And remember, x is the variable because it's an unknown. It can change. We can input values for it. It doesn't have a definite value right now. So the exponent of this x is going to be 2. And the exponent of this x is going to be 1. In regards to this -1, we can pretend it pretty much has an x next to it, but it's an x to the 0. And remember, any number n to the power of 0 is going to be equal to 1. So that's why this x to the 0 is equal to 1, and 1 times -1 is just going to give you -1. That's why we just have a constant here. So you can pretend there's an imaginary x to the power of 0 here, and I'm just going to put x to the 1 here. So we're going to look at the exponent of each variable, and we can determine the degree. Remember, this is called a polynomial here. In this case, it's a quadratic. The highest exponent is the degree of the polynomial. In this case, the term with the highest exponent is the 7x squared, because 2 is greater than 1, which is greater than 0. This is the highest exponent of the polynomial. So this polynomial is going to be like a second degree, so it's going to be a quadratic. We determine that by looking at the highest degree. So if we go back here, classifying polynomials, this is done by using the degree of the polynomial. So in this case, the degree of the polynomial is the highest exponent in that polynomial. In this case, it was the 2, so it's a quadratic. We can also classify it by looking at the number of terms there are. Remember, terms are pretty much going to be numerical values separated by addition or subtraction. In this case, the terms in this polynomial here are 7x squared. Then you have a plus sign here. Then we're going to have the 8x to the first power. We're going to have a minus sign here, and then we're going to have the 1. So this polynomial has 3 terms. Remember addition and subtraction. If you look here, the 7x squared is technically, if I expand it, it's 7 times x times x. However, the 7 and the x's are separated by multiplication, so that doesn't count as separate terms. They're all grouped into one term. Terms are separated by addition and subtraction. So therefore, this polynomial can also be classified by saying it has 3 terms. There's a better mathematical way to classify these polynomials, which I'm going to be showing you in the future, but that's just a basic understanding. We classify these polynomials by looking at the degree, which is the exponent of each variable, comparing them and determining which variable has the highest exponent, and that will be the degree of the polynomial. And then we also look at the number of terms that the polynomial contains. That's an overview. Let's look at polynomial standard form. So here's the key concept that I want you all to keep in mind. The standard form of a polynomial function arranges the terms by degree in descending numerical order. So I want you all to remember standard form of a quadratic. Remember, standard form of a quadratic is y equals ax squared plus bx plus c. In this case, a, b, and c are coefficients. In this case, c is a constant because it doesn't have a variable attached to it. Remember, when I say constant, it's a value that does not change. So in this case, c can be any real number we want if we're working in the real number system. It just doesn't have an x with it. So it could be a +1, a -1/2, whatever we want. However, it doesn't have an x, so no matter what, it's not going to change. Therefore, if you look at ax squared plus bx and we apply that same principle, these guys have x's. Therefore, they will be subject to change depending on what we plug in for x. If we look at this and you refer to this descending numerical order, how are we going to organize these polynomial functions? So we're thinking about arranging them in terms of degree. So if we look at this quadratic, the quadratic standard form, we have ax squared. If we look at the degree of this term, remember the terms are separated by addition or subtraction. In this case, it's addition. This ax squared is raised to a degree of 2. This bx has a degree of 1. Remember, there's an imaginary 1 here. And the cx is raised to 0. That's why the x to the power of 0 is 1, and then c times 1 is just c. If we look at descending numerical order, that means that we're going to have the highest degree, so the term with the highest degree, in this case it's ax squared, to the term with the lowest degree. That's what descending numerical order is. If we said ascending numerical order, we're going to be starting with the term with the lowest degree and then going to the term with the highest degree. However, the right way to organize and arrange a polynomial is start with the highest degree and then work towards the lowest degree. That's why proper quadratic standard form is written as ax squared, where you put your x squared term first, then you put your linear term, which is your x to the power 1 term, and then you put your constant last. So let's apply this to a polynomial, p of x in standard form. So p of x is shown here. P of x, remember, is a function. It can be written again as y equals, or f of x, which you're probably more common with. Same thing. So p of x is a polynomial, and this is how you would write p of x in standard form. The first term is a with a subscript of n times x to the power n plus a subscript n minus 1 times x to the power of n minus 1 plus this dot 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 just means a bunch of other terms. And then you're going to have plus a subscript 1 times x plus a subscript 0, and then the polynomial ends. I'll explain exactly what each of these means. So n, keep in mind, is a non-negative integer. So n means it has to belong to, if you're looking at like a set, n belongs to real integers, but n has to be greater than 0. So n can be 1, 2, 3, 4, 5, so on. Can't be a fraction, and it cannot be negative. If it's negative, then what happens based off of exponent rules is you're going to flip a number into the denominator, and it gets really messy. And if you use fractions, then you're going to have to bring in radicals, and it just also gets messy. So for our case, for polynomials, you're always going to have n as a non-negative integer. And remember, n is the exponent that x is raised to here at the beginning, and then it's just going to be the exponent here again. You'll also find it in the subscript, and I'll explain why it's found in the subscript. If you look at a here is the coefficient. I'm going to underline it. Coefficient. In this case, it's a constant because of the last term. A of n, a subscript n, dot, 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 meaning all the terms between them, and then a subscript 0 are supposed to be real numbers. And remember, real numbers, anything that it doesn't include imaginary numbers, I. So they can be any numbers we want. These subscripts can be any numbers we want. Unlike n, they don't have to just be non-negative integers. They just have to be real numbers, meaning they cannot be I. I'm just going to write that here. They just cannot be I, so they have no other restriction at all. So let me better explain this. So the first term you're going to see is going to be a with a subscript of, I can't even speak, subscript of n times x to the power n. So n is going to be just any non-negative integer. For example, let's pretend n is 4. So let's pretend this here is going to be a quartic term. So let's pretend it's like, let's say we have 7x to the 4th plus 3x cubed minus x squared plus 2x minus 5. I just made this up off the top of my head. So let's pretend in this case n is going to be 4. So this is going to be the first term. Then we're going to have the next term in the sequence, and it's going to be n minus 1. Since we said n was 4, 4 minus 1 is 3, hence we have our cubic term. We're going to keep going. And then this term right here, this n minus 1 is going to give us 2. 2 minus 1 is going to give us 1. Pretend there's an imaginary 1 here. 1 minus 1 is going to give us 0. 5x minus 5x to the power of 0, because x to the power of 0 is 1. 1 times negative 5 is negative 5. So that's how this works. So you're pretty much going to have a situation where you have n, and depending on what n is, every term that comes after it is going to be raised to a degree less than the previous term. This is really polynomial standard form in its most perfect sense. You're going to have, if you start with a power of 4, you're going to have a power of 3, then a power of 2, then a power of 1, and so on. There are going to be instances where you're not going to have, maybe you're going to be missing certain terms. Maybe we could rewrite this as 7x to the 4th minus x squared. Maybe we don't have a cubic term. There's going to be instances like that, but we're just talking about perfect polynomial standard form. We're going to see another example right here. We're going to have another example where it says p of x equals 4x cubed plus 3x squared plus 5x minus 2. In this case, the 4x cubed, if you look at the exponent, compared to the other exponents in this polynomial function, the cubed is the highest one. That's why it's the degree of this polynomial. So therefore, 4x cubed is going to be the highest one. So we put it in descending order, 3, 2, 1, 0. 4x cubed is the cubic term because of the 3. 3x squared is the quadratic term because of the 2. 5x is a linear term because of the 1, and then negative 2 is a constant term because it doesn't have any variable attached to it, so it's not going to change depending on whatever value we input for x. Lastly, I just put this in a small box. So in the next video, when we're going to be doing practice, like I said, in the next video, we're going to be focusing on a lot of XY tables, which is a practice problem that is going to come up. And I remember I had to do multiple on the assessment I had to take off of this lesson. And what's going to happen is you're going to see XY tables and you're going to have to determine what function is represented. What do I mean by what function is represented? Well, you're going to have to determine what the degree of the polynomial is without being given the function, meaning you're not going to be given this p of x right here. You're just going to be given an xy table of values, and then you're going to have to look at the corresponding values, and you're going to have to determine the function, how the function value decreases or increases between y values. You calculate how it increases or decreases, however it fluctuates, and then using that, we have to be able to determine what the degree of the polynomial is. We're going to have to be able to tell, is this a quadratic we're looking at? Is this a cubic? Is this a quartic? Is this a quintic, etc.? Just by looking at the XY table. And I'll show you in the next video when we actually do the practice problem. It's better to do practice problems with those rather than just trying to give you notes on it. Okay, so now let's look at an identification table to help us better organize this information and better understand how exactly do we classify polynomials. So in this first column, we're going to have the polynomial given. So it's pretty much, you can imagine there's p of x equals x minus 3. P of x equals 7x squared. So this is going to be the polynomial. Here we're going to determine what the degree of the polynomial is. We're going to classify by degree, so we're going to use a more mathematical term to describe it. We're going to figure out how many numbers are in the polynomial, and then we're going to give it a mathematical term based off of how many polynomials. Okay, so the first polynomial we're given is just 4. No variable, no nothing, just 4. So what is the degree? Remember how we said whenever we have a constant, you can imagine that there's an x next to it, but that x is raised to 0, and that x to the 0, remember, any number to power 0 is equal to 1. So this pretty much equals 1, so 4 times 1 is just going to be equal to 4. Well, that means that the degree of the polynomial is going to be what that x is raised to. In this case, it's 0, so the degree is 0. We classify this by degree. Remember, constant is going to be any term without a variable, so we just call it a constant. Number of terms in this polynomial, well, you don't see any addition or subtraction here, so there's only this one term, which is 4. And if we have to classify it by the number of terms, remember the nomial part that comes after that is pretty much, I like to think of it as number or number of terms, so that nomial is going to follow anything: monomial, binomial, trinomial, polynomial. So monomial means 1. Just keep that in mind, 1. Monomial means 1, binomial means 2, trinomial means 3, and polynomial can mean 4, and so on. I'll explain exactly how we're going to differentiate. So in this case, since we only have the constant, it's only one term in this polynomial, it's going to be a monomial. Okay, let's move to the next one. Y equals x minus 3. In this case, the degree is equal to 1 because we have an x, and we can imagine if we just have an x and we don't see any exponent, it's raised to a power of 1 because any number raised to the power of 1 is equal to itself. 2 to the power of 1 is 2. 5 to the power of 1 is equal to 5, and so on. So in this case, the degree of this polynomial is just going to be 1. Now let's classify it by the degree. Well, if you have an x to the power of 1, it's going to be a linear term. Remember, y equals mx plus b. This looks a lot like that. So you can think of it like the linear terms we've worked with. So this is going to be linear. If we look at the number of terms, well, we see one subtraction sign in here. So the x is going to be its own term, and the 3 is going to be its own term. So there's 2 terms. Remember, like I said, bi means 2. So we're going to classify it as a binomial. Next, let's look at the 7x squared. Let's first classify it by degree. We have an x term here, so it's definitely not going to be a constant. If we look at the exponent, the x is raised to, it's a 2. Therefore, it's going to be quadratic. Whenever you see a 2, it's going to be a quadratic. If you see a 1, linear, 2, quadratic. Therefore, it's going to be quadratic, like I just said. Now to determine how many terms there are. Well, we don't see any plus or minus signs. You can think of this 7x squared as, like I said before, 7 times x times x. However, each of these are separated by a multiplication sign, not an addition or subtraction sign. So this wouldn't count as 3 different terms. They're all considered a single term. Therefore, we're going to have one term, and we've already seen this before. That's going to be a monomial. Next, you're going to see y equals 3x cubed plus 9x squared minus 5. Let's first determine the degree. Luckily for us, this is already arranged in descending order. So if we look at each of these terms here, because we see an addition and a subtraction sign, so this here is one term, this here is another term, this here is the third term. If we look at the exponents for each one, we have 3x to the third cubed, which is the exponent is 3. 9x squared, exponent is 2, and then we have a 5, just a 5. So we're gonna obviously see that this is an x to the 0, so that it's a 0. It's already organized in descending order, and remember, if we have multiple terms, we find the term with the greatest exponent, and that is the degree of the polynomial. So in this case, the 3x cubed has the greatest exponent, so we're going to call this a third degree, and it's going to be a cubic because 3 is cubic. Then we're going to look at the number of terms, like we just said, there are 3, so it's going to be a trinomial. Remember, tri means 3. Next, we're going to look at y equals 6x to the fourth plus 8x squared. In this case, we also have two different terms. See, they're separated by the plus sign. There's a 6x to the fourth and an 8x squared. This one is raised to the power of 4. This one's raised to the power of 2. 4 is greater than 2, so the degree of this polynomial is going to be 4. 4 is quartic. So that's probably not as common to you, so I'm just going to run through them. If it's 0, constant. 1, linear. 2, quadratic. 3, cubic. 4, quartic. 5, quintic. And then so on. I wouldn't worry about the larger ones. You might encounter them, but I wouldn't worry about them. So because it's a 4, it's quartic. So to determine the number of terms, we got 2. 2 is binomial. This last one here, it's a bit longer. I wanted to challenge all of you. So this first one is going to be negative x to the fifth minus 5x cubed plus 2x squared plus 1. We see a minus sign right here. Keep in mind that this is just a negative sign. It's not a minus sign. This is a minus here. This is a plus here. This is a plus here. Therefore, we have 4 different terms. Luckily, again, this is in descending order. So we have this one raised to the power of 5, this term raised to the power of 3, this one raised to 2, and then this one's obviously just raised to 0 because it's a constant. Because 5 is greater than 3 and 2, this polynomial's highest exponent is 5, so its degree is 5. 5 is quintic. Then we got to determine the number of terms there are. There are 4, like we said, and 4, you're going to call anything greater than 3 terms, anything greater than a trinomial is going to be a polynomial. Even if you have 5 terms, 6 terms, 4, anything greater than 3 is going to be a polynomial. What I like to do is write polynomial, and then underneath it, I'll always write parentheses, and then I'll say of 4 terms, because here we had 4 terms. If it has 5 terms, polynomial, parentheses of 5 terms. I always just do that to clarify to my teacher that I know exactly how to classify this polynomial based off of the number of terms it has. So just keep that in mind. Next, let's look at end behavior, which I hinted at the beginning. So end behavior is the degree. End behavior is affected by the degree of the polynomial. So the degree of the polynomial, meaning the highest exponent of the term with the highest exponent in the polynomial, that exponent is going to affect the shape of the graph when you graph it on a TI or by hand. It also determines the maximum number of turning points in a graph, and I'll explain what turning points are. So a turning point is when you see a graph change from increasing to decreasing, meaning it's going up, and then it goes down. So the point where it changes direction, the point where it kind of goes increasing and then changes to decreasing, that is called a turning point. You can also think of increasing as rising because you're going up, and decreasing as falling because you're just going down. And I'll draw something very quickly after I explain this. Or it can go in the opposite direction, so vice versa, where a graph originally starts off decreasing, and then it turns at this turning point, and then suddenly starts going up, increasing. So it goes from falling, almost like nosediving, if you want to think of a plane, nosediving, and then suddenly the pilot pulls up, and then it immediately starts shooting upwards, so it starts rising. So I'm just going to sketch a graph of just a random polynomial, something like that. So this polynomial would have 2 turning points. The first one would be right here, and then the second one would be right here. That's because the polynomial was increasing as it approached this turning point. As soon as it met this turning point, it suddenly started going downward. And it kept going downward until it met this second turning point, and then immediately changed direction and started going upward. So that's simply what turning points are. They're really not complicated. If you turn, you're switching direction. So if you want to think of it that way, and there are only 2 directions a graph can go, other than it just being constant. Let's think about the 2 directions as being increasing or decreasing. So a turning point is when it changes from one to the other. These turning points will also affect end behavior. And to give you a clear definition of what end behavior is, it's the directions of the graph to the far left and to the far right. So if we're going to look at this little sketch I made again, the directions of the graph to the far left, and then the far left would be over here, and then the far right would be over here. So we're trying to focus on where is this arrow going, and where is this arrow going? Well, the end behavior to the left, we can see that this graph is actually steadily decreasing, but as it approaches the turning point, it is increasing. The graph over here, it's steadily increasing. So as it moves away from the turning point. So that's what end behavior is. It's pretty much seeing where the ends of the graph go. And I'll show you better examples on the next slide. So you're going to be focusing on the very far right of the graph and the very far left of the graph in your view, whatever viewing window you have. And you'll look at those ends to determine the end behavior of the polynomial. Okay, so let's go to the next slide. I'm going to be showing you a table so that we can better organize this information. So let's look at this first part of the table. This right here, this here is going to be a quartic polynomial. A quartic, as you can see, I've actually written the equation for it down here. It's y equals 4x to the fourth plus 6x cubed minus x. This is written in descending order because 4 is the term with the 4x to the fourth, is the term with the highest exponent, which is 4. The 4 is even, so I wrote even up here, and as you can see on the graph, there are 3 turning points. The first one is okay, let me quickly change my pen color so that I can show you. Okay, I changed my pen color. So if you look down here, this is going to be your first turning point. This is going to be your second turning point. And this is going to be your third turning point. And I've written it down here. Turning points negative 1.07, negative 1.04, which is here. And then you got negative 0.27, 0.17, which is here. And then you have 0.22, negative 0.15, which is here. We're going to be able to see how the polynomial is decreasing when we look at these different intervals. So we're going to write it in terms of like inequalities. So the polynomial is going to be decreasing when x is less than negative 1.07. This right here is where x is equal to negative 1.07. So when x is less than that, we're talking about this segment. So this segment is decreasing, so it's moving downward. And that's where the polynomial is decreasing. Another area where the polynomial is decreasing is when x is equal to negative 0.27 and x is equal to 0.22. So it's pretty much this interval right here we're talking about, because if you see, this is also going downward. This right here is 0.22, and this is negative 0.27. If you see, we write this in terms of the domain, which is x, so keep that in mind. That's how you determine where the polynomial is increasing and decreasing. There are also 2 intervals where this polynomial is increasing. It's right here. It's getting a little bit busy, but right here is where the polynomial is increasing. It is between negative 1.07 and negative 0.27. So that's where the polynomial is increasing. And then the second place the polynomial is increasing is over here. It's where x is just greater than 0.22. So it's just going towards positive infinity. Okay, so let's look at the next one. This here, you can easily see that this is a parabola, should be common. This is y equals negative x squared plus 2x. If you see, the coefficient is a negative 1 because it's negative. The parabola is flipped over, reflected. So if you look at the exponent again, it's a 2. So that is even. That's what I wrote up here. And there's 1 turning point, which is going to be the vertex right here. Because if you see, the parabola is actually increasing as it's moving towards the turning point. And then suddenly it changes and it starts decreasing as it's moving away from the turning point. So the turning point itself is the point 1, 1, as you can just easily tell from the graph. We can tell that, like I said, the polynomial is decreasing as x is getting larger than 1. So x is equal to 1 right here. As x increases, the polynomial, you see, starts to decrease. The value of the polynomial decreases. So as x increases, y is going to decrease. As you see, it starts going into the fourth quadrant, which has negative y values as x increases. However, the polynomial, this quadratic, is increasing as x approaches 1. As x gets larger, the y value is also getting larger. So that's where it's increasing as x approaches 1. Okay, so let's look at 2 more of these. Next, these two are special because they're both odd. So if we look here, this is a this is a parent cubic function. It's y equals x cubed. The cube is odd. That's why I wrote it up here, because 3 is odd. And there are no turning points in this graph. It's an exception. I'll show you why. If you see, you don't see any error. You see this graph. If you always read a graph left to right, like a book. If we start down here, this graph starts down low, but it continues to increase. Then it hits somewhat of a plateau right here, but that doesn't mean it's decreasing. So it's going to increase until it hits this somewhat of a plateau, and then it's going to continue increasing all the way to positive infinity. So nowhere is it decreasing. It doesn't change direction at all. To have a turning point, you need to go from increasing to decreasing or from decreasing to increasing. However, this function simply does not do that, so it has no turning points, which I wrote down here for you. If we look at end behavior, we're going to look at the ends of this graph. If you see, it's going upward here to the far, so it's going upward here, and then it's going downward here. That's why we see down, because it's down here to the far left. We read it like a book, so left to right. It's down here, and then it's up here. So that's why we say down and up. For decreasing, it doesn't decrease at all. This function, like we said, just keeps increasing, so it's decreasing for no values of x. But however, because it's increasing just infinitely, we see it's increasing for all values of x. So the next one we're going to look at is another cubic. It's y equals negative x cubed plus 2x, so it's reflected, and it has a linear term attached to it. So we're going to see how this is a bit different. If we look at end behavior, so to the far left and then to the far right, you see opposite to this one, on the far left, we're all the way up here, so we're up. On the far left. On the far right, we're all the way down here, so we're down. So that's why we write up and then down. The turning points, this actually does have turning points, because you can easily see that this cubic is, if you read it from left to right, it's decreasing, and then suddenly it increases, and then it decreases all the way to infinity. So it's decreasing when it's going to be decreasing in two places, from negative infinity all the way to negative 0.8 when x is equal to negative 0.82, and it's also going to be decreasing when it hits 0.82 all the way to infinity. And we're talking about x values here. The only interval where it's going to be increasing is this interval right here, between negative 0.82 and 0.82. So that's the only place you're going to see this increasing. So those were the end behavior tables. So now let's talk about end behavior and its relationship to coefficients. So instead of having to just look at a graph, if you're not able to look at a graph and you're only just given the polynomial function, you can still determine the end behavior without even looking at the graph, just by looking at the leading coefficient using this following table. So the leading coefficient, I'm just going to write polynomial. Standard form plus bx plus c. So this x squared right here, because it has the highest degree, this is going to be your leading term. It's going to be the first term. So that's what we mean by leading term. If we're talking about leading coefficient, we mean a. So we're going to look at how we determine end behavior of a polynomial function with leading term, this ax to the power of n. A is your coefficient, x is your variable, n is your is your degree. We're going to assume this is the leading coefficient. We're going to assume this is the term with the highest exponent in the whole polynomial. So if you look at this table, if a is positive, meaning our coefficient is positive, and the n value, which is this exponent right here, is also even, but it can't be equal to 0. Make sure it's not equal to 0. If it's equal to 0, it's a constant, doesn't count. Remember, if we have something like a constant, if it's just y equals 7 or y equals 5, it's just going to be a horizontal line. There's going to be no increasing or decreasing, no up and down. So we can't use a constant at all. So n cannot be equal to 0. So if n is even and a is positive, the graph is going to be up and up. So you can think of a parabola up and up like this. If a is still positive but n is odd, like a cubic, it's going to be down and then it's going to go up. And we're reading this from the left to the right. If a is negative, so there's a negative sign in front of a, but n is even, it's going to be down and down. So we can think of a parabola but reflected. So it'd be something like this. And then if a is negative and n is also an n is also odd, it's going to be up and then it's going to come down. It's a bit hard for me to show you with my fingers, but all I would say, I hate saying this, but you're going to have to memorize those. They'll just come in handy if you don't have the time to like sketch a graph during an assessment, and if you just want to look at a polynomial and be able to tell what the end behavior of it is. Okay, so that's all I have for you today. I hope you enjoyed. If you did, please like, subscribe, hit the post notification bell, share using all our socials, and also comment down below. You can also check out our website and email us with any questions, requests, etc. To connect with us. Thank you for watching and look for the next Algebra 2 video.